Hello everyone, my name is Sergey Kachkin, and in this presentation I'm going to share our experience with porting Linux kernel tracing tool called LinuxKI to OpenPOWER platform. We'll cover the motivation, so why you may want to port something to OpenPOWER, especially if you are not a professional programmer like I am. What things you need to do during porting, how to deal with platform-dependent components, and how to fix kernel panics, because this tool contains kernel module, and when you port a kernel module, panics happens very often. There are many Linux performance tools already available on OpenPOWER, so you can simply take them and use for your performance problem. Why you may want to invest your time into porting one module? Well, for me the answer is that with LinuxKI I can resolve performance problems faster and easier. My colleagues and myself will have good experience of using LinuxKI on other platforms and want to have the same on OpenPOWER. Most of other performance tools, they cover some specific subsystem, and you can run different tools with different parameters several times and then correlate one tool with another tool. With LinuxKI, you can collect data once, build static reports, and then get good understanding of what happens on the system. And often it helps to better understand what is the root cause of a performance problem. The LinuxKI has two parts. The kernel module is responsible for capturing traces and sending them to user space. It uses default Linux tracing mechanisms like static trace points and kprobes. This module needs to be loaded only for a short period of time while the tracing is enabled. You don't need to have it loaded all the time. The user space part reads data from the kernel, and then it can store data to disk for offline analysis and building reports, or it can build reports online, so you can use LinuxKI as observability tool. Please visit GitHub. You can find their masterclass and video tutorials. Actually, this is a very well documented tool. Let's talk a bit about possible challenges we may have during porting LinuxKI to OpenPOWER. First of all, it contains a kernel module with some portion of low-level platform-dependent code. It needs to be ported. I'm not writing kernel code every day, and this part can be challenging. On the other hand, LinuxKI already available on x86 and ARM, so I can use this code as a reference. Additionally, most of the code, especially user space part, built successfully on OpenPOWER with no changes, and I just need to make sure that it provides right data. So, during porting we have an easy part and more challenging part. The easy part will contain adding some if-defs to align includes and swap some x86 and ARM functions into OpenPOWER ones. And also we need to align a system call numbers, because on different platforms the same system calls may be presented from the kernel space into user space with different numbers. A more challenging part will contain porting stack and wind code, which is platform dependent, and also we need to debug panics because we are porting kernel module, and we need to be ready to meet them. Most challenging part of every porting is low-level platform-dependent code. In LinuxKI, we have a portion of such code, unfortunately. This is a stack and wind or backtracing code. The question, why we can't just drop this and use LinuxKI without this feature? Let's talk a bit about this. Stack unwinding is used for on-CPU and off-CPU profiling. It allows us to do analysis similar to flame graphs. Everybody loves flame graphs, and definitely we want to have this feature in the tool we are porting. So, what options we have to get it? We can write the code from scratch. It can be difficult. We can grab the code somewhere in Linux kernel from OpenPOWER, and we can use ARM or x86 code as a reference and use it. Let's have a look at stack and wind algorithm more detailed to get a better understanding how to port it easier. The result of stack unwinding or backtracing is a call stack of functions. This call stack is used for on-CPU profiling, and it helps to understand what the system is doing when it's busy. And also it's used for off-CPU profiling. It helps to find out what the system is waiting for when it's idling. Actually, these two questions are the main questions of each and every performance analysis. The basic idea of stack unwinding or backtracing is actually quite easy. We need to find the current stack frame where we are. We store instruction pointer. Then we follow the pointer to find the previous stack frame, store instruction pointer, and again while we can get something useful. The requirements for unwinding is we need to do it very fast. At the same time, we can lose some stack traces because we collect hundreds and thousands of stack traces during profiling. If we fail this one, hopefully we will be successful next time, and the result of profiling will give us what we need. Initially, I reviewed the Linux kernel for OpenPOWER and built my own version of stack unwinding, and then I compared what I got with ARM code, ARM unwind code, which already exists in LinuxKI, and found that the code is very similar. And then I compared the tail of stack frame for ARM and for PowerPC, and noted that they are very close to each other. So I dropped my code and reused the code for ARM with very small changes. The lesson I learned is that, well, it's obvious. Before writing something, look at existing code. It may save you time and you do not need to run extra miles. Now let's move to the next part of the presentation, is troubleshooting panics. Actually, this part took, I don't know, maybe 85% of the whole time needed to get a working code. I decided to show 3 different panics. One of them is relatively easy, another one I called intermediate, and the third one is, I called it crazy, because it was really difficult to find the root cause. Troubleshooting the first panic was relatively easy. The reason is that the panic happens in LinuxKI code. We can see it in the stack trace. The very top functions point to liquid module, which is LinuxKI kernel module. So we know where the root cause is located. So it means that LinuxKI is doing something wrong. And on the other hand, the Vim core, which is generated during crash, contains some useful data which can be used for troubleshooting. So we have at least 2 options to find the root cause of the panic. We can review the Vim core with crash tool or any other tool, or I don't know, for me it's harder because I don't do it every day. And another option, we can add some print case to our code. We know the function which where the panic happens, and generate the panic and look at Linux log, and it gives us very good understanding what was the root cause. I decided to take an easy way. I added some print case to the function where the panic happens. I generated the crash, I reviewed the logs and found the root cause. That was quite easy. The root cause is that we have a regs structure. We try to fill it, and then we dereference it. If the structure is empty, during dereference, we're getting crash. We try to fill the structure from a task_pt_regs kernel function. Somehow, on x86, this kernel function always returns something valuable. For PowerPC, it may generate nothing, and we're getting panic. I don't know why it happens, but it works like this. The solution is quite easy. We just need to handle that return value maybe nothing. What I've learned from here is that the same kernel functions may behave differently on PowerPC and other platforms. Let's move to the next panic. I called it intermediate. It's more difficult than the previous one because the panic happens not in LinuxKI code, so it happens somewhere else in the Linux kernel. It means that the module we're porting breaks something in the kernel, and then some kernel subsystem hits the problem and we get the crash. If we're lucky, vim core, which is generated during the crash, can be helpful, and we can open it with crash tool or any other tool and get the root cause of the problem. If we look at backtrace, I don't know, for me it's meaningless. So I can't get any conclusions from this and need to go deeper into the vim core and open it with a crash tool. I opened the vim core with the debugger and I was lucky because crash tool does some basic verification of the kernel structures in the vim core it opens, and it printed some errors. These errors looked like a kernel corruption to me, and I got the structure names and their location. What I can do as the next step, I can print the structures that look corrupted and see the pattern of the corruption. In this case, I was lucky because the corrupted memory pages contained instruction pointers, pointers to text. It gave me a hint that somehow stack unwind algorithm corrupts memory because only stack unwinding or backtracing deals with instruction pointers. Somehow we store them to the wrong address. And I reviewed the unwind algorithm in greater details and found the root cause. It was found that there was a code change in Linux kernel 4.7. The structure called perf_callchain_entry, which is used for storing instruction pointers, have been changed. Before Linux kernel 4.7, it had pre-allocated array for 127 elements for storing instruction pointers. Starting version 4.7, it has 0 size. So LinuxKI tries to write instruction pointers into the array and corrupts the memory beyond the structure. The problem happens on all platforms, but somehow only PowerPC panics. So x86 was just lucky that corruption doesn't affect anything important. The fix was, well, actually I just reported the problem to the maintainer, and he provided the fix for all platforms, including PowerPC. What I've learned from this: we live in wonderful Linux world when kernel structures may be changed silently anytime, and you may know this only when get a kernel crash. The only way to avoid such panics is to test your software against each and every kernel version and be extremely careful when send your code to customers or run on some critical systems. All these things may be obvious to professional programmers who write code every day and know all these details about Linux kernel development. But for me, that was something new. And if you are in similar position, you need to take such things into account when you port something to OpenPOWER. Let's move to third panic. I called it crazy because it happens outside of LinuxKI code, so we can't instrument our code with print case and debug the problem. On the other hand, the vim core seemed useless. I spent many hours looking into vim core with debugger, and it didn't help to reach the root cause. I don't know, probably I did something incorrectly. And the panic happens in the interrupt processing code. Somehow interrupts were enabled at point where they should be disabled. It means that LinuxKI module have been called, it did something, left interrupt in a wrong state, and later some kernel code checked the interrupt state and got a panic. So at moment of the panic, the initial event which caused the problem is gone. I spent a long time with looking into the code, discussions with my colleagues, with the LinuxKI maintainer. It didn't help because panics happens only on PowerPC and never seen on x86 or ARM. Finally, the only way to get the root cause was to disable everything or kernel module functions and then enable them one by one until we get a panic. So that helped to isolate the root cause. Finally, it was found that JProbes are causing panic with such strange symptoms. JProbes are used in LinuxKI for on-CPU profiling. They are deprecated in the latest Linux kernel, but still exist in kernel 4.12, where the panic was seen. Somehow, JProbes work on x86, but do not work on PowerPC. And the solution was quite easy. We just moved from JProbes to a new mechanism for recent Linux kernel where they are deprecated. I don't know what I've learned from this experience. I don't know, maybe just improved my debugging skills, and unfortunately when porting tools to OpenPOWER you may hit such problems and need to deal with them, and better to be informed about this in advance. Finally, we made LinuxKI working on OpenPOWER platform, and hopefully it will be merged with upstream soon and available at GitHub at the same location with other platforms, ARM and x86. We did some amount of testing and verification, fixed some panics, but definitely there is a wide area for further testing and code improvements. This work showed that porting such tools, which includes kernel low-level components to OpenPOWER, is doable even if you are not professional programmer. It can be challenging, but it's doable. And in this presentation, I showed possible problems that you may hit and some ways how to approach them. And so thank you very much for watching, and I'm ready to answer your questions. Thanks.